Hi guys, and welcome to the second week, basically, of the second part of the second week of this astronomy late start. We are in section 71, I believe it is. Yeah, this is our section. So this is astronomy 120. Last time we basically covered units 5 and 6, and we even up to, I think, 7. We need to cover units 8 and 9, especially has to do with the what we mean by the lunar month and things like that. So this is basically what we're going to be covering through these two units, namely unit 8 and 9. And also unit 8, as I mentioned last time, is of a great importance because of the fact that it will have an immediate impact on our project. So I want to make sure that you guys have full understanding of what that means and how to get things done to do that. Okay. So that is really the whole point of today. And so that's, don't forget, we also have some assignments. One of them is due today, another one is due on Saturday, a few of them actually due on Saturday. So make sure that you're actually on top of those. You will receive reminders from me. And also you have a quiz this week that you're supposed to also be taking care of. So this is in terms of the assignment. So let me dive into the content of this week. Let me first of all find the units 8. I'm going to jump first to unit 9, okay, because it's a little bit, yes, unit 9, because it's a little bit kind of continuation of the stuff that we're talking about. So let me go share unit 9. So here are the objectives of Unit 9. So Unit 9 is explain the historical and astronomical origins of the week and the month. Again, this is our attempt to divide basically time into chunks that we can manage. And based on that, we have this idea basically of the time. First of all, the day we decided to be 24 hours. Then we followed the month basically. Namely, its origin is coming from the word moon. That's where the month is. The moon takes about 29.5 days, so it's about 30 days, basically, on average. So we divided the year into 12 equivalent, basically, more or less, times of called months. So we have 12 months. The thing to remember in here also, as far as the week, the idea behind the week, yes, the idea was floated at some point of 10-day week and some other ideas, but then now it follows the most known objects in the sky that we knew of at that time, okay? I know some of you speak Spanish in here, so when I say these things probably in French, it's very close actually to Spanish. I have had this experience before with my students, and it's very, very close. And I'm going to point out the ideas in here for how the week came to be basically 7 days and what in each and every one of those days represents. And then the calendar, it depends actually right now on different cultures have different representations of a calendar. The three main different calendars right now that exist is the one based on the solar calendar, which is the Gregorian calendar. But also we have non-Gregorian calendars. Sometimes they follow culture, sometimes they follow religion. For example, Islamic religion, they have the lunar calendar, which they follow. And also we have the sometimes for the Jewish, for example, religion, also for the Jewish culture, and also for the Chinese culture, they use a mixture of the two between the lunar calendar and the solar calendar. So this is actually some of the things. And then the idea of the leap year, because the Earth does not really do 365 days a week, every year around the sun. The rotation is actually 365 and a quarter of a day. So what we decided to do is add a quarter and a quarter and a quarter 4 times to make up an additional year in a leap year. So that's how the February at times is 29 days, and sometimes, most of the times, 3 years in a row, it's only 28. So those quarter from the first year add up to the quarter of the second year, add up to the quarter of the third year. By the fourth year, you have already 4 quarters to make up a full day. So now you have a leap year in there so that the calendar stays in its place. Otherwise, it's going to shift because of the fourth day. Okay. So that's basically the whole point of this thing in here. Obviously, this is important. I mean, keeping a tab of time has important in the old culture, especially, for example, for agricultural purposes, for religious celebrations and things like that. So that's why it has a practical need for it. It's not just something that we decided to do on its own. And that is, again, has to do with how the Earth moves around the sun. Okay, so that is in a nutshell what that is. So let me first of all jump into the, again, so these are some of the different representations in different cultures. Okay, so the 7-day week was adopted by the Babylonians, and before them the Sumerians, and it has to do more or less because of probably how the moon goes around the sun. I mean, around the Earth, I'm sorry. The moon goes around the Earth in 29.5 days, but it goes through a 4-cycle system that we're going to talk about in Unit 8. Moon goes from the first cycle, basically growing from when it's barely above the horizon after the sun sets, barely a crescent, and then it starts, that crescent starts to grow and grow and grow until 7 days later, or 7.5 days later, a week later, basically, it becomes a quarter moon, meaning at that point, first of all, it rises higher in the sky, and then you can see it after the sun sets, and you're going to see it in the middle of the sky around midnight, and then it's a quarter moon. It's going to set at that time following the sun, and the night will be completely dark at that time when it sets, and then the sun rises from the other direction. So that is a week period to go from a no moon at all, which called the new moon at that time, to a quarter moon. Then the moon starts to continue to grow in its size and rising further and further to the east now when the sun sets. Okay, earlier and earlier in the night also as the sun sets. And that growth takes about a week until at some point it's completely, when the sun sets, the moon rises and it's all lit. Okay, that is a full moon. Again, all of those things are part of Unit 8. But the idea in here, it takes about a week to do that process, to go through that process. It takes another week to go from being a full moon, basically, to another quarter moon pointing in the opposite direction, though. Okay? Remember, it starts growing this way, and now it becomes this way. The bulging is on one end, not on the other. Okay? And it takes another week to disappear again, and the cycle repeats. So that's probably where the idea, again, of the week came from. But the point being in here is that this is the cycle of how these things are. And but then came the naming of those days of the week, because remember, 24 hours is a full day. So we have to name them accordingly. So I know some of you speak Spanish in here, and probably they can understand this one. Probably most of you do, but I wish I do. Sorry about that. But I can tell you the words in French, and they should be very, very similar. Okay, so let me stop sharing the screen. And let me, first of all, prepare the other one before I share it. 20, so yeah, we're still in week 2, so I can use this slide in here. So share. Okay, so here is the idea. We knew then of the following objects that go around the sun. Around the Earth, I'm sorry, because we didn't know that the Earth was moving around the sun. So we know Mercury actually is one object, and we know Mars is another object, and we know also Jupiter is another object that is visible in the sky, and also Venus and Saturn. In addition to that, we know also of the moon going around the Earth, and we know also of the sun going around the Earth. Okay, so the sun, not sun. Okay, so those are the objects that go around the Earth that we know of. Since conveniently the moon does that behavior in about a week, which is 7 days, in about 7 days. So this unit of 7 days was divided into this number of celestial objects that go around the Earth. So here is the idea. We came up with a day that corresponds to the sun, and we called it the day of the sun, namely Sunday. I mean, it's telling from here. The moon also has acquired a day, which is the day that follows. The day before them is actually the day of Saturn. Okay, so that's clear from the naming that what they're related. Mars actually has to do with Tuesday. I know in French, Mars is actually mardi. And I'm not 100% sure how to say it, but I think also in Spanish it's very close from this word too. So it has to do with the day of Mars. So
I think Tuesday is martes.
Martes, so it's very good. So it's close enough, okay? They're both Latin languages, so they should have close enough way of saying it. But that's the day of Mars. So Tuesday is actually the day of Mars. That's what it should translate to, day of Mars. Remember, in Greek mythology, all of these things, they have some symbols and they were worshipped and things like that. As a matter of fact, the next day, which is Wednesday, that is the day of Mercury. Okay. And again, in French, it's Mercredi. And I'm sure also in Spanish is very close.
Yeah,
Who
so
helped me with that? Go ahead.
it's miércoles and then it's jueves and viernes.
Okay, how do you spell Mercules? I-C-O-L-E-S. Did I spell it correctly? Yes.
Oh, I think.
Did I mess it up? Sorry. Okay, I know in French it's Mercredi. Okay, sorry about that. But the point being, they are similar. Both Wednesday is actually the day of Mercury, and Jupiter is actually the day also of the. In French, it's actually jeudi. That's the day of Jupiter, and I'm sure you said it in Spanish, but I can't remember it. So this is actually Thursday. There is actually God in the Germanic cultures that has also Thor in it, and that is actually Jupiter himself, okay? So again, that is the day of Jupiter. And then finally, Venus, which is in French, vendredi. And you said something about then something like that. That is actually similar to it. That is Friday. That is the day of Venus. You see how these things, they fit together? That's how we decided the names of the week are. This was convenient. We didn't know about the other two planets then. We didn't know that a planet called Uranus existed. Otherwise, we probably could have a day for it. And Neptune too. Uranus was discovered by Herschel later on. And that was in the 1800s. And then Neptune was actually calculated based on Uranus's odd behavior, that there is a planet that exists out there, and that planet has this specific location. So sure enough, the astronomers in Germany at that time, when they pointed their telescopes, and later on in England, they found that planet Neptune. So it was purely found by calculation. And that calculation is actually based on Newton's, Kepler's laws. So that's how it was found. That's Neptune. But Uranus was discovered by Herschel, actually, who, after several days of looking at it, he noticed that there is actually another planet with a telescope. That's how he found it. Okay. So those are the other two planets that are not part of the scheme, that are not part of the naming, because they were not known then when the weeks were devised and everything else. So those are basically the weeks of the days of the week as related to the objects that move around the sky. Mercury and Venus are always either ahead of or behind the sun. Venus is the brightest star by far, and Venus has a name, which was the morning star, and at the same time the evening star, and it was actually had some significance in other cultures. Okay, thank you very much. So I messed it up. Sorry about that, okay? So Mercredi is Miercoles. Very good, thank you. And so that's the point in here that we have to remember in here. So that's how the naming of the weeks came about. So let me go back into stop sharing the screen now and share with you Unit 9. So that's how the 7th day of the week are. Now, the moon actually takes 29.5 days to go around the Earth. It's not exactly 29.5, some change also, if you want to be picky about those changes in there, okay? So the actual motion of the moon and is actually, and we're going to discuss that, it takes only about 27 1/3 of a day. So this is the actual rotation of the Earth around the moon around the Earth. But the Earth itself is moving, so the moon has to actually do an extra 2 days to meet with that same phase, okay, for whichever phase that we have. As I was saying before, the month actually, in some cultures, they use completely the moon. This is the lunar calendar according to the Islamic calendar, and this is from the year 1426, which would correspond to 1995 or something like that. What is something like this? Okay, I think right now we are in the year 1444 or so, 45 or something. So the lunar calendar is slightly different, because of the fact that the lunar calendar is based on 29.5 days to be more exact, and the solar calendar is actually on average it's more 30 days or more, sometimes 31 days, sometimes 30 days, granted sometimes 28 days, but in all there is an 11-day difference between them. So there is a 365 days for the solar year, the number of days for the solar calendar, and there is 354 days for the lunar calendar. So this is the solar calendar. The lunar. So there is an 11-day discrepancy between the two. Okay. Meaning that the lunar calendar moves back in time. So it's not fixed at the same time. For example, this month, Safar, for example, it could be in the summer. Right now it's in March, April. Next year is going to be actually moving back, okay? That's why if you know the Islamic holidays, they move. They are not in the same. Ramadan last year was in one period. Next year is going to move closer to moving from the summer, for example, to the spring, from the spring to the winter, from the winter back to the fall, and it's going to rotate. And it's going to rotate exactly about 33 years, okay? It's going to come back 33 years. It's going to come back to where it was before because of this discrepancy between the two calendars. Obviously, some cultures they didn't like that very much. So what they decided to do actually is to combine the two and add the 13th month, excuse me, to fix the calendar. To fix the calendar, and those are the Jewish and the Chinese calendar. Okay, so they have a mixture of these two, so that the calendar doesn't rotate. The calendar stays fixed in the year. Okay, so that is the idea behind this calendars in here. Okay, so again, the story behind it goes way back into how it was adopted. Sometimes there was a discrepancy, and especially the week at some points it was a little bit off. We're not really interested in the history as much as interested in the astronomical observations right now, honestly. But the idea of the leap year, again, I mentioned it at the beginning, is because there is a quarter day. If you really count how many, what's the length of the solar year compared to the number of days. So what you do in this case, you introduce the leap year. And there are some rules about the leap year. The year has to be either divisible by 400. So for example, 1900 is not a leap year. 2000 is a leap year, because 2000 divided by 400, that's going to be 5. Okay, but 1900 divided by 400 is not going to be 5. It's going to be 4.75. Okay, so this year is not a leap year. That's one thing. And then after that, you add every 4 years, you add to them, it becomes a leap year. So 2004 was a leap year. 2008 was a leap year. 2012 was a leap year. 2016 was a leap year. 2020 was a leap year. During the 2024 was a leap year, and so on and so forth. I need you to remember these dates in here because there will be a problem that we're going to be discussing when it comes to the lunar eclipse, and we need to know when to make predictions for the lunar eclipse. So we need to account for the leap years when we're doing that calculations. Okay. So again, this is the Gregorian calendar and has some interesting dates in it. And earlier it was starting in February, and then the 2 months were added at the beginning to make up for the discrepancy to make it 12 months. Okay. Okay, so this is in a nutshell about the calendar. Please don't forget that you're supposed to be doing the reading of the book in here. Okay, there was a couple of problems today with my previous class. So I'm hoping that you guys, if it happens again, somehow if the internet hangs or something, please don't leave, okay? So let me share with you the next unit, which is actually a very important unit that you guys need to focus on. That is unit 8. So I started backward in a sense today. We did unit 8, 9, and then we're going back to unit 8. So again, this is about the cycles of the moon, and I really want you guys to pay attention to this unit because it's a very important. One of the major objectives of this class is to learn about the moon phases and describe the period that we are in the lunar month based on the phase of the moon when you look at it. And you will have a project, as I was saying, and the project is going to open up sometime next week, where you're going to be monitoring the moon for 4 weeks in a row. And each time you go out, you're going to decide on how the moon looks like, so that you're going to answer questions basically related to that, okay? So identify the phases of the moon and explain their geometry, predict when and where the moon will be in the sky, depending on its phase. Describe when and where solar lunar eclipses are visible. So that's important. We need to understand when we're going to have a solar eclipse. Obviously, we'll have a solar eclipse when the sun is gone during daytime. So what blocks it is the moon. So the moon needs to be between the earth and the sun. When are we going to have a lunar eclipse? Well, it's happened at night. The moon is at night, and you're going to lose the moon all of a sudden, or at least most of it. What is going to block its light? It's the earth, actually, that sits between it and the sun. So the question is, during the new moon, when the moon is just barely born, that's the only time when we could technically have a solar eclipse. And during a full moon, that's the only time technically where we could have a lunar eclipse. The question is, why don't we have both every month? Because we have these two phenomena every month. And that has to do with how the moon moves around the earth and how the earth moves around the sun. In other words, the apparent motion of the sun around the earth and the real motion of the moon around the earth. So the apparent motion of the sun around the earth and how the earth is moving and how the moon is moving around the earth. Well, these two planes are not coplanar. They are not in the same plane. One plane is sitting this way and the other plane is like this. So they cross each other at an angle. And the moon moves in its orbit around the earth. When the two orbits cross, you will have a lunar eclipse and a solar eclipse on that month. Okay. When they are far away, then you don't have them. That's the answer in a nutshell to the question, okay, which is part of the discussion that you have for this week, okay? And then explain why eclipses do not occur every month. That is the answer to the question, really. Okay, the only reason why they don't occur is because the two planes sometimes they cross each other, and that is when you will have a lunar eclipse and solar eclipse. Or the moon could end up far away on this side or far below on the other side. So if it's far below or far above, and it's a full moon, of course, the radiation from the sun is going and filling the entire sky and hitting the moon and coming back to us, and we're looking at a full moon. Or if the moon is on the other side, new moon, and the sun is on the other side, shining its radiation throughout the, blanketing the entire, basically, sky for us during daytime, and the moon is there, but the radiation is well above, so it's not going to block the sun. So in this case, we don't see the moon. This is a new moon. So that is basically why we don't see it most of the time, either above or below the ecliptic. So that's why we don't see it. But when it sits right in the right position, then we will have a lunar eclipse or a solar eclipse. Okay, so again, the phases of the moon, as I mentioned in the beginning, the moons go through basically different phases in a 4-cycle period. So when it's a new moon, because it's in the sky, but you don't see it because the sun is basically there, you don't see anything. Early in the evening, though, you start to see a faint, after the sun sets, immediately where it's setting, somewhere in the west side where it's setting, there is a faint crescent. And that crescent starts to grow every night. Okay, so we call this one a waxing crescent. So waxing in this case is increasing in size, and it's a crescent. And it's pointing in the direction from where the sun is setting. So the sun is in the west, so the lit part in here is going to be in the west. So if you see the lit part of the moon is pointing to the west and the dark part is in the east, then you know that you are in the beginning of the lunar month. This is the first week of the lunar month. Then, after 7.5 days, basically, the moon will have, after the sun sets, it's going to be in the sky, and it's going to have half of it, or quarter of it, I should say, full. I mean, for you, you're looking at a sphere. So half of the sphere is lit, and the lit part is pointing to where the sun is setting, which is the west, and the dark side is pointing to the east. So this is the first quarter. Okay. So it has grown completely from a crescent, nothing at all, to a tiny crescent, and that crescent kept on increasing until half of the moon is lit, and that is actually a quarter, which is the first quarter. How do I know it's the first? Because the lit part is pointing toward the west. Day later, it's going to continue increasing, and it's always the lit part is pointing toward the west and the dark side in here, and there is a bulge that starts to form in this case. We call it a gibbous. And this gibbous is increasing inside, so it's a waxing gibbous. That's what the name for it in here. And that bulge keep on increasing until about 15 days, 2 weeks later, basically, the entire moon is lit now. And as the sun sets, it rises in the east. The sun sets in the west, the moon rises in the east. So in this case, it's a full moon. All of the moon is lit at that point. Okay. So there is no east or west that is lit. The entire thing is lit. Now, it's going to start shrinking now. And the lit part now starts to point to the east, not in the west. The sun is still setting in the west, but the moon now is actually being chased now by the sun. Okay, so the sun, the side that is lit, is actually in the east, not the west. So now we are in the 3rd week of the lunar month. At this point, there is a bulge, but bulge pointing in the opposite direction, and it's shrinking. So it's a waning gibbous. Waning means it's fading, and the gibbous is that shape. Okay, it's trying to shrink in here until only half of the moon is lit, and the half that is lit is pointing to the east. Actually, now we are in the 3rd quarter of the cycle, the lunar cycle. We are in the 3rd quarter, as opposed to the 1st quarter, where the east side was the one that is lit. Now, I mean, where the west side was lit. Now we are in the east side being lit. So this is the 3rd quarter. As time progresses during this entire week, the shape changes from the 3rd quarter to now a crescent, but crescent pointing in the opposite direction. Instead of the lit part in the west, the lit part now is in the east, and it's shrinking. So it's a waning crescent. And it's going to continue shrinking in size until there is only a faint crescent left. The next day, there will be no moon. Okay, actually, a new moon We lost this one, but we have a new one that is coming. The king is dead, long live the king, basically. That's the same story in here. So we have the new moon that starts and the whole cycle repeats again. Make sense to you guys? Okay, very good, thank you. So it's important that you guys understand this slide because it summarizes everything that we need for everything else. And in here, in the second picture that I didn't talk about a lot, it shows the position of the sun, the earth, and the moon for every single phase, provided that the earth and the moon are, the earth and the sun are fixed. This is what's going on. The moon is the only thing that is moving, okay, in this situation. Remember, the earth does 365 days to go around the sun, but the moon does it in only 29.5 days. So the moon is moving faster around the earth than the earth is moving around the sun. So in the new moon, the moon is between the earth and the sun. And you don't ask me why we don't have a solar eclipse, because of the fact that the moon doesn't necessarily is not on the same plane. It's sitting either above or below that plane. So it's not blocking the sun for us. So we still have a full day with no solar eclipse whatsoever. Solar eclipses are extremely rare, especially the full ones, okay? So they're extremely rare. So it has to be perfect alignment so that they will have that solar eclipse. And if they happen in our region, they don't happen necessarily everywhere in the world with the same intensity at least. Okay, so this is the new moon. And as we progress in here, it's going to be a waxing crescent until we have a first quarter. First quarter is that the sun is shining on it and we are at a 90-degree angle looking at it. When it's, so the other side is not lit. When it's on the opposite side, and again, don't tell me why we don't have a lunar eclipse, because they are not on the same plane. The moon is either a little above or a little below, so that it's receiving all the radiation from the sun, completely lit, the entire circle is visible, and that is what we mean by the full moon. And then, actually, it's so bright at that time that you can probably pull a book and start reading. That's the point, that to explain the extent to which this thing is lit, okay? Then it starts to fade now until we have a quarter again, but it's pointing in the, it's always pointing in this direction, to the direction of the sun, but it's actually which way is rising and which way is setting. That's really the point, why it flips in here to us, why you see it differently in here, okay? And then you go through the entire picture again and again and again. So if you are in the third quarter, this is how it looks like. If you are crescent pointing in this direction and the sun is in this direction, then you're looking at this position in here and not that one, and so on and so forth. Okay. Let me talk a little bit about the lunar cycle and how long does it take. Okay, we're looking at the new moon in this picture. And we are in position 1. So there was a new moon in here. We decided a lunar month lasts from one phase to the same phase next time around. So the new moon, the next new moon is the new lunar month. That's basically what it is. So when the sun, when the moon is actually between the earth and the sun, exactly. So when we look at the moon and the moon in there, so we don't see any kind of shadow on any side of the moon, left or right. Okay, so that is the new moon. Gone. We don't see it because the sun is basically overwhelming the entire sky with its color. Okay, so in this case, when the moon completes a full cycle, goes around the earth, which is 27.3 days, we still see part of it because the sun is actually coming in here to us and we see the moon and it's not in the same direction. So the earth needs those extra 2 days to continue moving, and the moon continue moving those extra 2 days, so that the moon also sits between the earth and the moon, and the earth and the sun, I'm sorry. So in this situation, this is what the difference is. This we decided to be 29, this we measured it to be 29.5 days, and this is what we decide to be the lunar month. The sidereal month, which is the actual rotation of the moon around the earth, which is exactly how long does it take for the moon to go full cycle around the earth. This whole thing is only 27.3 days. Similar to what we did with the solar day, and the sidereal day. Sidereal day is with respect to the stars, the same thing. The lunar month is with respect to the stars, faraway stars that we don't move with respect to at all. So if you look at the moon in a specific constellation, and if you want next month when it's in that same position, that is only 27.3 days. But if you're looking from phase to phase, from the full moon to the full moon, or from quarter moon to the quarter moon, or third quarter to the third quarter, or new moon to new moon, that is 29.5 days. That is because the Earth is moving around the sun. Okay, that is basically the whole reason behind it. Again, this is a picture explaining exactly what we were talking about. As the sun sets, the sun is still here, just below the horizon, and the moon is just following it in here in this location, because remember, they were completely next to one another, but the moon is moving toward on the Earth a little bit faster than the Earth is moving around the sun. So in this case, they will separate, and as they separate, the sun will cast its rays on it, and we will see part of it in a crescent, and that crescent will keep on increasing until 7.5 days later, which is about 8 nights later, you're going to see the quarter moon. Because now it's a completely it's a 90-degree angle between the triangle that is formed. If you wait 15 days as the sun sets, the moon is on the opposite direction because it's on the other side completely of the Earth sun system. Okay. Okay, so the point in here is that this is the idea behind it. So the same thing in here, this is how the moon would look like on the different days. And it's going to be actually visible later on in the afternoon in the sky. And in here, actually, it's going to be visible in the morning, later toward the week, toward the lunar month, I'm sorry. So again, this is when it's going to rise. In the beginning of the lunar month, it's going to rise in the west. That is midnight. Let's take midnight in here. So midnight is going to be setting actually in the first week, especially when it's a quarter moon. So a quarter moon will set in the west. Okay. On day 22 at midnight, actually the moon is, when it's third quarter, is going to be rising, and the sun, remember, is rising behind it too. So because we are in this case midnight and the sun is coming on the opposite direction, so as the moon moves away, the sun is going to catch it. So when the day comes in, the moon is still in the sky. Okay. And when it's a midnight, when it's a full moon, 15 days later, it actually covers the entire night. It goes from the beginning to the end. When the sun sets, the moon rises, and it's going to stay all the way at night until when the sun rises, the moon sets. That is when it's a full moon. So at midnight, it will be in the middle of the sky. So that is basically the idea behind it. This picture in here is the opposite of this one, in a sense that in the 28th day, the 15th day, so the sun rises. As it rises, the moon sets, and this picture will keep on increasing. On the 22nd day, as the sun rises, the moon is still in the middle of the sky, in the horizon, well above the horizon. And then later on in the month, as the sun sets, the sun rises, the moon barely is basically rising also, and the sun is catching it. That's why the rays are actually coming from the east. That's why the lit part is actually the eastern part in the second half of the lunar month. That's why you see this picture in the lunar month when it's toward the end. Okay. Again, this is a summary of these things in the terminology that is used. So when you're doing your project, please use the correct terminology at the end. Although, oops, what did I do in here? I moved things. Where is my keyboard? Okay. So this is a waxing crescent from day 0, from the new moon, to about 7.5 days. Around 7.5 days, it's a first quarter. Then it's a gibbous now, it's increasing and bulging. And that's from 7.5 days to about 15 days. So it's a waxing gibbous. Around 15 days, it's a full moon. And it's a waning gibbous from that time on all the way to about 3 weeks later from when the whole thing started, 22 days. And then it's a third quarter from 22 days to around 29.5 days, okay? So that is something, you're asking and wondering how in the world are going to do a lunar month with 29.5, because either 29 and 30, that you're right. because a lunar month actually, and that is from the lunar calendar from the previous unit, is actually sometimes either 30 days or 29 days, because to account for this discrepancy. Okay, so let me find the lunar calendar that we looked at earlier. Okay, so let me stop sharing to show you the point that I was talking about. I know we went through it without discussing this point here. So you see here the lunar calendar, this one is 30 days, this one is 29 days, this one is 29 days, this one is 29 days. So again, because actually it's 29 and a half, so it fluctuates a little. The lunar month, they fluctuate a little bit. So it's a composite because there is no 29 and a half lunar, month in the calendar. So you really have to do full day. Same thing with the lunar, with the solar, basically sidereal, with the solar, leap years, because we have 395 and a quarter. So every 4 years you compensate for them. Same thing is happening actually with the lunar month here. So let's continue this one. It's important to understand the phases, which brings us to another important point, and that is the solar eclipses. Okay. The plane through which the Earth moves, this is the ecliptic, the one in blue. The plane through which the moon moves is not the ecliptic, is offset by about 5 degrees. So it could be as far as away from the sun by 5 degrees above or 5 degrees below. But when it's not, when it's exactly on that same plane, it produces a shadow. Okay, and that shadow is the shadow of the moon on Earth, hiding the sun behind it, and it's going to show us the corona of the sun. So this is a solar eclipse. For this region, for a region away from it, if it's on the same line of the site, it's going to receive it later on. But if it's away, they may experience partial solar eclipse, but not full one. But other regions may not even see that. So that's a region sensitive, really. Okay. So again, the shadow of the moon is cast on the Earth, and that is what the region is. So this complete umbra, which is the basically stands for the shadow, is where you have the full solar eclipse. And then you have the region before it, penumbra, is the one that gives you partial solar eclipse. Okay, partial eclipse. So those are the two distinctions in here. Okay, this is the shadow of the Earth, also it's an umbra, and it could have a full lunar eclipse if the moon, when it's full moon, is actually inside the shadow of the Earth. Again, that's a phenomenon. I need you guys to remember this picture here because it kind of come in handy later on also for one of our problems that we're going to discuss extensively. And the problem, this is basically the next, from the publication of this book in here, I know 2020 last happened a long time ago, 2019. So this is past and future. So these are part of the lunar eclipses. The 2017 actually happened to be in the Midwest, and that was a fun one to watch because it passed through Missouri, and I was in there at that time. And it happened here in California too, and it was beautiful, but it was not as full solar eclipse as it happened in the as it happened in the Midwest. That's the region of total eclipse. In 2024, April 2024, which is 2 years from now, basically, or a year and a half from now. It's going to be in also the Midwest. So if you have a chance to go to be in Texas or anywhere also in the Midwest, all the way to New England, that's also a good place to be on that time. Okay, April 8th, we have school, so probably we'll have to manage somehow to do that. Okay, there are some interesting things that are at least accessible to me. One that's going to happen in Spain and Portugal and actually Eastern Europe, that is in 2026. And there is another one that is actually close by also in Africa, Northern Africa, that is going to be on August 2nd, 2027. Okay. So, and there are others in here, 2023 in Australia, or what is it, the oceans, and then 2028 in Australia, and so on and so forth. The point being in here is the one in Australia is going to be in July. That's actually a very good thing to plan to go to if one can go to Australia and see it too. We're going to use this chart in here to make a prediction on when the next total solar eclipse is going to happen somewhere in here in Southern California, Mexico, and all of this region. This one Based on the Mayan calendar calculations, we will be able to predict when is the next total eclipse is going to happen. And you will see a fun way of doing it, okay? Again, lunar eclipses, they happen in the same fashion with the exception of two things. First of all, the moon is in the shadow of the earth, not the other way around, okay? The moon is not blocking the sun. And it happens when it's a full moon. So it cannot happen in any other case. For the full moon is when it's in the position and with the earth and the sun, they all form one line. The other condition for it also, the other thing that you need to notice is the shape of the moon. The color of the moon changes from white, basically bright object, to a reddish object. So you ask, where is that reddish color is coming from? And it's because of how the rays of the sun gets deviated when they hit the atmosphere of the earth. This is the same reason why the sunrise and the sunset, they have that reddish color in them. It's because of the same reasons, okay? So the same phenomenon is associated also with the moon. So what's going on in this situation is the earth is blocking the rays of the sun, but the atmosphere is acting as a lensing effect. So it's taking the rays and bending them. And as they hit the moon, they hit it in this radiation. Because red light is a longer wavelength, okay, it bends first, and the blue light actually scatters. Okay, that's what's going on in here. That's why you have the red light is coming to the moon, and we see it reddish in color. By the way, this difference between the red light and the blue light is the reason why the sky is blue. Because during midday, as the rays of the sun come through the sky, the rays of the sun, the red lights, they're going to be deviated. Basically, we're not going to be seeing them as much as they should. But the red light scatters every which way more because they're coming straight out. And that's why the sun actually appears, or the sky appears blue. And the same reason why the oceans have basically acquired that color, as a reflection of the sky, that's all. During the nighttime, during the evening, it's the opposite. Actually, the blue light is scattered, and we don't see it, but the red light is actually coming through, in this case, bending through the atmosphere and coming to Earth. By the way, when you look at the sun rising or setting, and you see it in the horizon, that is actually not true. The sun already is still below the horizon, because the rays, here is the sun, the rays are coming from the sun, and we don't see the sun either during the rise or the set when it's setting, but the sun, the rays are coming straight and bending to us, giving the impression that we see the sun, and we see it. But we're looking at bending light that is coming from the sun. And it's that long wavelength red light that causes that. So when you go in the evening and you look at the sunset, and you see that beautiful color of the sun, and the sun, it's actually has already set, okay? So you're looking at the after effect because of this phenomenon, exactly that causes the moon to be red in color, okay? So again, there is the partial and the full, again, because of the penumbra and the umbra. Again, the same phenomenon, because the moon can be completely full lunar eclipse or partial. And this is what I was talking about in here. When can we expect to have a lunar eclipse or a solar eclipse? It's when the moon is actually within a degree when its path, it's within a degree. Right now, it can fluctuate between a positive 5 degrees and a negative 5 degrees. So if it's a positive 5 degrees, and we're sitting in here in the Earth, this whole distance, 384,000 kilometers, so it's far away. So the rays of the sun will hit it and reflect back to us, and we will see, we are in the night side in here, the sun on the other side, we're going to see a full moon, beautifully lit full moon. Now, if it's a new moon, it's on this side in here, okay? And again, we're going to see nothing, because the rays of the sun are coming in here, and they're lighting the entire side of in here, but this side is completely dark to us, and we're looking, this is daytime now, and we're looking and we don't see the moon because the sun overwhelms everything. Now, this path changes throughout the year. Sometimes this path is not as far as 5 degrees, but 1 degree. If it's 1 degree, then the moon will fall in that shadow. And if it's 1 degree in our region, then that shadow of the moon will extend to the earth and we will have a solar eclipse or we will have a lunar eclipse. That's the answer to that question. It's because of those two paths, they're not in the same, they're not coplanar. There is on and off, which makes it an interesting question to ask about, for example, the moons of Mars. There's 2 of them. Could they produce a similar phenomena? It depends on their path. Same thing for the moons of Jupiter. And Jupiter is huge, okay? But could they produce some sort of a solar eclipse or what? How? I mean, if you could stand on the surface of Jupiter, how would the lunar eclipse on any one of the moons of Jupiter, how would it look like? And vice versa. Or you could sit on one of the moons. So you'll have an interesting phenomenon if you could, for example, stand on the Europa, for example, which is the second big moon from Jupiter. Looking at all kinds of interesting phenomena, because you could have all the other moons on the opposite side and you can have a bunch of things going on if it's possible. But that depends also on these angles too. So you could have perfect alignment and nothing is visible to you because of this shift in positions, okay? So that is really what causes the different, if you wish, moving back and forth and things like that. So again, this is the same thing explained in here. Interesting thing in here that if you have a solar eclipse, you will have a lunar eclipse on the same month. Okay, so this is one of the phenomena that is true here. So this is in a nutshell, it's 2 units. And the project, I'm going to post it next week. Okay, is going to deal specifically about this one, but it's going to be a field up project. So although you are not required to do labs for this class, but you are required to do projects, okay? So you're going to be going for 4 nights in the month, okay? On specific dates that I'm going to publish to you, that I'm going to give you. And you're going to go and look at the moon to identify, first of all, its shape. Describe its shape. How does it look like to you? Half of it is lit, or most of it is lit, or all of it is lit, just part of it is lit, or I couldn't find a thing. I looked everywhere. Looked early at night, in the morning, it's not there, okay? And barring all weather conditions, so if there is a weather problem, we have to work around that. So just the moon, we know it's there somewhere, but we couldn't find it. We looked early in the evening, we waited for late in the evening, we looked early in the morning, we waited, nothing. There is no moon. That's probably because you are looking at a new moon, okay? Then you're going to name that phase now, depending on which side that is lit, depending on which side that is dark, depending on how much of lighting you have, you're going to name that phase. Is it a waxing crescent? Is it a waning crescent? Is it the waxing gibbous? Is it a waning gibbous? Is it a quarter? Which quarter is it? First quarter or third quarter? If it's a full moon, it's a full moon. If it's a new moon, it's a new moon. Okay, you can't really say anything more than that. But that is basically your task. And then the other thing also, you're going to tell me its position. First of all, where you are, because you may not be in where I am at. You may not be in Redlands and Loma Linda area. You may be somewhere else. You may be behind the desert, or probably even visiting with friends somewhere else in Arizona or somewhere else. So your location matters. So I need to know that, okay? The other thing also is the location of the moon. Is it toward the west, east, somewhere in between the east and west? Is it to the south? Is it to the north? Is it with the horizon in the east or the west? Or is it the horizon with the north or the horizon with the east? Or is it closer to your zenith in any of those directions? Or somewhere in between, midway? So I'm not looking for exact numbers. I'm just getting some sort of a sense of the approximation, in this case, locations. So that is basically your project in a nutshell. Obviously, we're going to talk more about it once you get the instructions with it. So right now, you don't have instructions, but I want you to connect it to this unit 8 so that you will have at least a reference point to come back to and be able to complete your task. Sounds good, guys?
Yes.
Okay, very good. So I'm going to stop the recording right now, and I will see you guys next week, okay? Same time. For those who are watching it recorded, please also follow the similar instructions. Thank you, guys.